Oh, kia ora koutou. Welcome to session three. This afternoon we have some deep learning and some uh, Plexi cloud infrastructure that we're going to find out about. So first up, I will remind you that we're going to be taking questions through the live Q&A. We have three full sessions this afternoon, taking us through to 5 o'clock. So without further ado, our first speaker is Dr. Brent Martin, talking about deep learning and real world problems, balancing opportunity with responsibility and dodging the hype trap. So, over to you, Brent.
Kia ora koutou everyone, ko Brent Martin toko ingoa. I'm a data scientist at Manaki Whenua Landcare Research, and what I wanted to do this afternoon was share some of the lessons that we've learned the hard way about what happens when you use cutting edge technology like deep learning out there in the real world and how you do that responsibly while still getting some business. So at Manaki Whenua, we've been working with deep learning for probably about 5 years now. Almost exclusively computer vision, and most of that around areas to do with mapping. And to begin with, it was just experimenting, seeing what could be done, and how we might move things forward, which is all fun and games. But eventually, we had to get serious and start applying it to our customers' problems, which they were paying us good money for. And that's when life gets interesting because the customers come with their preconceptions about what they're going to get. And this could be everything from, hey, but we've heard about XYZ, they've used deep learning, they managed to do it, so you should be able to do this for very little money and guarantee us a result, right? At the other end of the spectrum, we get, well, we heard that XYZ tried doing that using deep learning. It doesn't work. It's all a con. Why are you even bothering? And somewhere in the middle is the reality, which we've taken a few years to sort of work out how to deal with that reality. So I'm just going to walk through a couple of case studies of, first of all, a couple of early projects where we did sort of have to learn the hard way about how you manage expectations. So the first one of those was the Parliamentary Commissioner for the Environment, who wanted to measure how urban green space is changing over time. So what they wanted to be able to do was take a sample of cities, Auckland, Hamilton and Wellington, nominally 1940, 1980 and 2016 or similar, and essentially to objectively measure the amount of green space in the cities and then to be able to make commentary on what's happened to it, whether it's going up or down and so on. However, sitting behind that general objective, they made it pretty clear they were wildly interested in mapping and that they thought machine learning was going to have something to do with this. So we thought, why not? We'll jump in and we'll give that a go. So the issue, of course, was that historical imagery of cities is black and white, first of all. So this can be got online, but it's just a bunch of images. In most cases, those images hadn't even been stitched together, apart from Auckland Regional Council, who had done a beautiful job of stitching all of the images together, but they had in no way made them analysis ready. So one of our team, David Pearman, did a fantastic job applying cutting edge technology to turning that into a beautiful mosaic that we can see on the right. But what he couldn't do anything about was the fact that this was still 1940s black and white imagery scanned off of actual film, very grainy and with all sorts of issues. So that led to the question of how we're going to map green space from this type of photography. So we pitched two possible approaches. The first one's sort of the obvious one. Maybe it's possible to directly detect what's green space and not green space in that imagery, but we weren't very confident about that. So we sort of said, we'll give it a try, but don't hold your breath. More likely, we thought we might be able to map in particular buildings and maybe other surfaces such as roads and patios and driveways and all that kind of thing. That seemed more doable. Well, somewhere along the way, somebody got a bit over enthusiastic, and the next thing you know, we were heading down the track of trying to directly map green space. So first of all, we had to put some labeling data together. So we had to go at whether we could just use RGB imagery, color imagery, to identify the green space. And by producing an index based on the green and blue channels, we got a reasonably good result that we thought would be good enough to train a deep learning network. And then if we then switch to black and white, we can use that labeling to train the network. Seemed a good idea. Unfortunately, it didn't work. In particular, once we got back to that 1940s imagery, the results were just absolutely terrible. It was just, we could not get it to separate out the green space from grey. And actually, when you looked at it up close by eye, in a lot of cases, you wouldn't be able to tell the difference either. The imagery just wasn't good enough. Okay, well, if we couldn't do that, we fell back to our original plan of trying to detect the buildings. So that's got to be possible, right? And if we can do that, then we would be able to get these maps of the building footprint, subtract it from likely green space, and take that as a proxy for the green space available. Well, actually, that turned out to be harder than we thought as well. We produced a beautiful model that could use black and white imagery to detect buildings if the imagery was modern imagery that was trained on Linz's building footprint layer. Unfortunately, when we tried to use it on the old imagery, once again, it just didn't work. And no matter what we tried to do to make the images similar or to tweak the model, we could not get good recall on that old imagery. So at this point, we're back to scratching our heads again and wondering if we're going to be able to do what they asked. And what we ended up doing was we decided we'd try the approach of weakly supervised learning. So the idea here is that instead of using 2016 imagery that matched the label data, we would just throw all the imagery at it and pretend that the labels were correct for it. Now, of course, they're not. And the example on the screen there gives a couple of really good reasons why not. First of all, on the bottom right, there are buildings in the labeling that didn't exist in 1940. The other circle there shows that there's a place where a building exists, but not the same building. And finally, if we look on the left-hand side, we can see that the labeling and the imagery doesn't match, doesn't line up very well. And that was a constant problem because of distortion, lens distortion in that 1940s imagery. But anyway, we thought we'd give it a shot. The idea was we would throw away all of the image tiles that just looked they were so far from the truth that they weren't usable, and anything that seemed reasonable we would use in training. And believe it or not, this is an example of an image we would have considered to be reasonable enough that we would use it. Finally, we got some success and it started to work. So there's a 1940s image of Wellington in the left-hand side. In the middle is using the model that was trained just on 2016 imagery, and it's terrible. And on the right, we've got our new model that was trained on all of the imagery. So even though the data was imperfect, there were a lot of stuff in it that was inconsistent, nonetheless it worked. And we got a really good output. That gave us our built footprint maps now, or layers that we could use, both to look at what the big picture was in terms of growth of the cities and the way that they were changing, but also to look in detail at things like how urban infilling, residential infilling was impacting the city's green space. And more importantly, we were able to then aggregate that in the way that our client wanted. They were able to write their report about what's happening to our cities, and everybody was happy. In parallel with that project, we had another project that was also hitting some headwinds. This was about whether or not we can detect predators in camera trap imagery. This is something a lot of people have been working on. It seems straightforward. You've got lots and lots of images. What species of animal, if anything, is in that image so we can throw away the ones we're not interested in? Again, the problem was perception, because there are statistics being bandied around out there, such as, for example, there's a database called the Serengeti database. It's got lovely pictures of animals in it, and the YOLO object detection deep learning framework can achieve accuracies of around 95% on that. Great, that sounds really good. Well, it turns out our client had been told about that 95%, and that was their expectation of what we were going to do. Unfortunately, trail cameras in New Zealand don't produce beautiful pictures of animals standing there gazing longingly into the camera. Instead, we get things like animals that are so close because they're trying to take the camera to bits, or poor lighting, or things like down the bottom center, you've got a couple of wallabies having a bit of a biffo, and that two-headed monster is a bit hard for the software to figure out what it is. So the reality was we were getting things like 70 to 75% accuracy, not 95%. So the first thing we had to do was go back to the client and say, look, we're sorry, but it's just not achievable what you're trying to do, but we'll carry on the research, we'll quantify what we can achieve, and we can get some ideas about how we different ways rather than just automating the image analysis. So that was okay. They accepted that. We got on and did a bunch of research. And then just at the end of the project, a bit of a game changer came along, a system called Mega Detector, which has been developed by Microsoft and others. And what it does is just generally identify and put a box around any animal in the image. So Mega Detector had been working quite well up until then, but the V5 model worked extremely well. And that's partly because it has New Zealand imagery in it. So suddenly we were getting detection rates of 98% plus. We could couple that, use that basically to crop the animals out. All we had to do now was train a classifier that could detect the species, which we could do to anything up to 95% accuracy for the classifier. You put the two together and we're up to something like 87% accuracy now. So another win. And so out of that, not only did we manage to change the perceptions of the client about what was doable, we then came back and pleasantly surprised them and said, actually, we have built you some software. We've got this thing called CamTrap NZ. It is a piece of software you can run on your local PC. If you've got a GPU, it helps. And that will sort your images and give you a bunch of information about what it thinks is in them. Also, there's a beta version of that model on the trap.nz website, so citizens who do trapping and monitoring at home are able to use that, and the whole thing has been very successful. So that's a couple of examples of where things were a little rocky and we had to go through quite a bit of pain. The next time we had another project to work on, we got a lot smarter about how we sell it to the client. So this one was the Lucas land use map, and this is the map that is used for things like monitoring the amount of carbon that's sequestered in New Zealand forests. So right out of the box this time, we said, first of all, this is going to be an experiment. We are not going to generate the next generation map for you, job done. We are going to do it in parallel with the generation of the new map, and then we can assess it and see how it went. We therefore set targets in terms of its precision and recall that were realistic and that we thought we could meet, both for predicting a 2016 map, so seeing whether it could regenerate it, and then predicting the 2020 map. And finally, we said, don't expect us to automate things from end to end, but you may get some useful tools out of it that can be used as part of the process. So that was a success straight away because essentially we were able to meet the expectations we had set. Not only that, first of all, when we regenerated the 2016 map, we found not only did it do a pretty good job, as in about 95% accuracy, but also that some of the differences between our predicted map and the real map actually turned out to be errors in the real map. And through this process, we managed to burn in 1,500 error corrections to the 2016 map, which bonus. It also turned out to be quite good for change detection in some areas, such as urbanisation. In the top right there, we've got a picture on the outskirts of a Mokoroa in the Bay of Plenty. The blue line is where it was, where the city was in 2016, and the pink shows that it has nicely detected all of the new subdivisions going on to the south of Mokoroa. And finally, we had another tool that one of my colleagues, Alexander Amies, worked on, which is around automation of the detection of deforestation. So all of these things was just by taking that view that we're looking for some small wins, not the big win. We had a lot of good achievement there. And finally, the other thing we learned was to look for ways in which you can reuse the models that you're building. So having built that model around the land use map, one of the species or land covers it detects is exotic forestry. So when we were asked about the ability to detect wilding conifers, we thought maybe we can use the same model. And again, we did some careful expectation crafting because the client wanted us to come up with a national density map of wilding conifers. We said, well, we can do one, but we're not going to guarantee the quality of it, but we'll quantify that. We also thought we might be able to use the approach to do things like monitor for whether or not their control had been successful and things like that. And so by setting it up this way, again, saying we can probably pick apart pieces of the problem, but we can't necessarily solve the whole map, we were successful and they were very happy with the outcome on that. And the last time that we met with them, they were busy talking about what are other ways that the model might help them in general with wild and conifer work, as opposed to just generating a map. So to conclude then, in the first instance, when we were first doing this work, we were having to battle against expectations. We learned some important lessons so that now when we go into any project, we begin by setting their expectations, making sure they understand how cutting edge some of this work is. We bake in regular communication. So they're going to see our outputs or some information about our outputs really, really often. We have more recently baked in stop-go milestones as well. So the client from the outset in the contract gets to choose. Maybe halfway through, we all agree that this is going nowhere and we stop it. And in fact, with the wilding conifers, what happened is that halfway through, we saw a better pathway forward and we agreed to change path, carry on in a different direction, which worked really well. We also regularly brainstorm with the client possible new ways of using what we're doing as we build it. So as the research unfolds, we get a better idea of what it's going to do for us. And finally, that idea of building upon your successes, look for new opportunities. If you see a problem that could be related to something you've already done, why not start there? Why not start where you can say, look, I already know we can do this and maybe we can improve upon it. And so finally, my message to anyone who's looking at doing this kind of work, even though it can be kind of heart-stopping at times when you're not sure whether you're going to deliver or not, if you be bold and dive in, it's well worth it. It's a very exciting research area, and you can get some really good results for your clients. Thank you.
Cool. Thank you very much, Brent. That's a very interesting talk. I will drag people's attention to the live Q&A. If you can start writing your questions in there, we'll give you a minute or two to see if some will come through. But in the interim, I'll start with one of mine. You touched on issues of the New Zealand context, I suppose, being missing from some of these image databases. Do you want to speak a little bit more about how that's improving and who's doing the labeling of that data?
I think it's improving in a number of ways. It's a problem right across the board, and it's not only that you can get models from overseas, but they're missing the New Zealand context. You can also get where something has been done overseas, and I'll give the example of mapping wetlands, where the New Zealand context is manifestly harder than most other countries, and so people put forward models to use, and then it turns out it doesn't work at all. I think the main reason that the labeling is happening here is partly because of the type of work that I've just shown you. There's so much more interest now in what we already have in terms of stocks of things like land cover maps. Anytime I talk about using something like the land use map or the land cover database map to train models, I find that lots of organizations are already doing that. So, and so they then refine it for a new domain, and then out of that you get new labeling.
Cool. We've had two questions come in so far. So someone says, fascinating talk, thank you. Does Mega Detector accurately identify whether an animal is in frame, but not which species?
That's correct. That's exactly what it does. So although the Mega Detector team have been doing a bit of work on classification as well, but their object detector is the really big thing. So and it's been trained on just hundreds of thousands of even species of animals from all over the place, and it's just really accurate at that. And the standard pipeline now is detect first, classify later.
Cool. And then the second question is really interesting talk. I was interested in the analysis of green space over time, and I was curious if you looked into similar but perhaps cross-domain applications, such as looking for positioning solar panels on homes.
Okay, that's an interesting one. Certainly hadn't thought about that. Um, I guess it might be one of a number of techniques you could bring to bear. There's a lot. So depending on where you're looking, of course, in New Zealand now, there's also an awful lot of LiDAR information, and it's getting better all the time, especially in our cities. And once you have LiDAR, you can do things like you can reconstruct the city in 3D, and then you can run models that will give you your sunshine hours at any given place. So we could potentially apply to that sort of domain, but I think there are probably there are possibly better tools out that can do that more directly.
Cool, thank you. Um, Once again, a great talk, highly interesting. Our next talk is going to be from Jun He and Kahu Anderson, and they're going to talk to us about introducing NeSI's flexible HPC, the cloud-native platform for enabling challenging solutions. Over to you, Jun and Kahu.
Thank you. Kia ora koutou. My name's Jun. I'm here with wonderful Kahu, who has recently joined NeSI as a DevOps support specialist. Today, I'll be talking about NeSI's new Research Developer Cloud. Notice the change in name in the last minute. It is a programmable cloud infrastructure where we can build things together for the research communities. And you may have heard Flexi HPC, Flexible HPC before across other talks, and Murray just now with our original submission title. It is the underlying infrastructure that we've been working on for the past couple of years that's trying to address to the demands around diverse needs across the sector, which is slight shift from our traditional HPC where you submit jobs and wait for it to finish and get the result. But the communities requiring more interactive and diverse solutions. So Research Developer Cloud is now our new name for the service layer where you can access these infrastructure as a service. And these are our initial offerings. So we are calling them essential building blocks. If you've used things like AWS, you'll be familiar with the concept. So we have compute where you can launch virtual machines of different flavors like high CPU or like high memory, but depending on the needs. And then we have tailored list of operating systems that you can use for images, and you can create your custom images and share with the community. And we have scalable storage space that can be used and various network options so that you could set up your solution to be visible to the internet in a secure way. So only particular ports or particular VMs have access to certain site or certain connectivity and so on. And you could create application credentials and control access to your project so that you could do any of the tasks programmatically, and everything has APIs. So we are really pushing for focused on delivering a great developer experience. And many of you probably have heard DevOps, but may not be too familiar with what it is. So NeSI has a team who's using many of the DevOps approaches. So it's a set of practices to help with collaboration and bring more visibility to the solution being built, and enabling rapid development and deployment, and enabling sharing your whatever you built with wider community and so on. So as some examples around DevOps practices, I'm sure all of you are familiar with using GitHubs to collaborate in the code area. And then you could use things like GitHub Action, which gets triggered when you push certain code with special tags or something like that, that could trigger automatic build and run some tests. And it could do CI/CD, continuous integration and deployment, so that things get, once the test passes, whatever your new commit gets released into the test environment or even production environment, and then and then things operate within a managed resources using tools such as Kubernetes, and then everything gets monitored, and then you capture the feedback and back to the plan and so on. So it's an ongoing cycle, and with who suite of tools and practices that you could use to improve your whatever you are building. And DevSecOps is a similar to DevOps, but including security in consideration. And Michael Carriage has given a really insightful talk earlier with Ned today. Please have a look at the recording if you missed it. But the whole idea is applying security measures in all steps from the beginning, and that it is not something that you tack on afterwards. And here's a bit of a rough high-level diagram of where what we are envisioning. So this is from our actually our annual review from activities from last year. So it is using slightly different terms, but we built a new platform with the help of global experts, and we have had collaborations with 4 different tenants as we were shaping up the services. And together we've been building various types of solutions that can help different research communities for different needs. And what we want to be able to do is collaborate with you and maybe start small by building something for your research group, but eventually we want to be able to share and have be able to impact wider research communities. I'll quickly go through a couple of examples. AGDR, Aaron's given a talk earlier on quite a bit of detail, so I'll skip most of it, but I'll just mention that we've used open source technology called Gen3, which is genomic domain specific data repository solution. And that solution, so that this is what it looks like. We have growing list of data sets for genomic data in New Zealand. And the Gen3 architecture basically has a whole bunch of small microservices that sits inside private network. And there's one web proxy service which passes on all the requests to various services needed. And these kind of things are very easy to deploy using our new services. And we have done some work to make sure these are run in Kubernetes so that things are scalable, monitored, and the health they are running healthy. Another example which is quite different is our collaboration with Ag Research, which is a much bigger scale institutional level collaboration to develop a whole suite of tools and services for ag research researchers. And there's been many different challenges around data migration and retaining their current identity and so on. And currently, Thomas and many of our team are working on building open on demand as a user interface for researchers to be able to access various services such as Jupyter and submitting. Just by the way, this is not an actual screenshot. I took it from Brown University's Open on Demand. So this is Open on Demand is a technology that allows you to access various other services, and most Open on Demand installation looks something like this. And this is our architecture where it shows different layers of our architecture that are more towards the back end and to the front end, and all of them sitting in different levels of network. And I'll pass on to Kahu.
Thank you very much, John. Tēnā koutou katoa. Kahu Anderson, recently working with NeSI on their research DevOps side of things. Now, one of the things, as John said, is we've been using the Research Developer Cloud to build certain components on top of that to empower the researchers. And for NeSI to get a head start on that, we decided to pick the training environment as our basically learning example. And apply those DevOps practices like Ansible and Terraform against that cloud-based system. The other thing it gives us the ability to do is in the future is provide training outside of NeSI. Now, we use the technology stacks, as you can see, Terraform being the orchestration within that system, and we use the Ansible to configure that system. Now, the Research Developer Cloud is based upon the OpenStack technology. So these are something that you guys can use, not just within the NeSI Research Cloud, but can also use them elsewhere as it is platform agnostic. Now, the architecture that we're looking at around the training environment is a standard Git repo, which then once you commit resources to that or do a commit to it, it triggers the GitHub actions, applies the Ansible and Terraform against the Research Developer Cloud, and provides the Open on-demand web node, which inside of that contains Keycloak, and then also spins up X number of Kubernetes control planes or workers, depending on the demand that is required for the training environment that you are looking for. Now, where we are now currently in regards to that is we have the basic environment set up that is also reproducible with Ansible and Terraform, and we base it off the Machine Learning 101 training environment or training module that NeSI provides. We want to get to the point where each training environment is deployed to its own domain, and then that means you can have more than one training environment, say within Auckland or Christchurch happening at the same time. And we also want the ability to self-provision training environments on top of our research cloud on demand. So it's not just reliant on NeSI to produce these things. One of the experiences that we've managed to gain from doing this is using Terraform to test the reusable code that we are talking about, not only on our own infrastructure, but others as well. And then, like I said, can be integrated within DevOps pipelines and actions. Now, one of the other experience we've taken is building upon that same Terraform example prior. We then use the Ansible modules and roles to generate the training environment. And the screenshot there is actually of the training environment and being able to spin up Jupyter Hub and Jupyter Labs, as well as remote desktops on top of those systems. Now, back to you, John, on the rest of that one.
Cool, thank you. Yeah, so those were some examples of our past collaborations, and we really want to invite you to apply for early access. And we're really keen to learn about what you wish you could build for your research communities, and if there are any gaps with DevOps skills and expertise, and what should NeSI be focused on next. You can apply and read more about the Research Developer Cloud at this URL here, nesi.org.nz/developer-cloud. If you go there, there will be an apply button, and please feel free to reach out to us at support@cloud.nesi.org.nz as well. And last but not least, we couldn't have gotten here without all the cool people here, and our early tenants who collaborated with us, and our infrastructure partners, as well as Rian's, who's provided the underlying high-speed network. Thank you.
Cool, thank you, Jun and Kahu. Very interesting talk. I will direct people again to the live Q&A to get your questions in. I'm sure there's going to be several of them. We'll give people a second while I wait for some questions. I have one of my own. How does this developer cloud, I suppose, fit into the context of, or how does NeSI differentiate itself with this developer cloud from the existing providers such as AWS and Azure? And how does it fit with the current allocation model of the collaborators and people accessing NeSI?
Right. So I think the key differentiator here is that we are trying to, we are looking for projects that we can collaborate with. So not something that is too simple, but with moderate complexity, and something that can eventually benefit the wider community. So we want to build that shared knowledge so that as we add more services, it might be more towards building a list of blueprints so that the solutions that we build can be used again. And if you contact us and if we see the project to be more fitting for Nectar, for example, then we'll definitely recommend you there. So yeah. And in terms of the allocation model, we are still trying to figure out, and there's one big thing that I forgot to mention, which is if you contact us now, I think we internally we've been saying we'll give 3 months free access, up to 3 months free access. So yeah, so if you have ideas, please apply now, and you might get some early access benefits there.
Just to also add on to what Jim said as well, is the big thing difference between, I suppose, NeSI and Azure and AWS is the data sovereignty issue that we have a lot of issues with as well. So being hosted with NeSI, it's onshore in regards to the data as well. So it doesn't leave New Zealand shores. Yes, so we do have the question in regards to how HashiCorp recently changed their license from the Mozilla public license 2.0 to the business source license. It will not impact us at all. You're able to use any of the other open source solutions. You could go towards the standard, what do they call themselves? Open Terraform or Terraform Open, I believe it was called. Or you can even use Pumel, I believe is another one that is being thrown around as well. So it's not just related to Terraform. Terraform was just one of those ones that we did use as an example for our leaning towards that. But you're able to use anything. If you really want to get hand down and dirty, you can also use just standard CLI commands to also do the same thing as well.
Thank you. So tēnā koutou. So we're jumping into my presentation. I think Murray has had some issues with his connection. So I'm going to be talking about our deep learning pipeline and Manaaki Whenua, but very specifically how we're configuring that. Apologies examples at after 4:30 in the afternoon today, but they're quite simple. So I'm sort of building on a presentation a colleague of mine, Jan Schindler, gave in 2021 at the same conference where he spoke about our pipeline that we call DeepSeg. I'm talking about what we're calling DeepSeg 2, and part of moving to version 2 was reworking the configuration of our deep learning pipeline. We also had other goals as well, and those are around sort of ML op goals, and those are around tracking our experimentation for our deep learning projects. And when I'm talking about deep learning projects, I'm very much talking about what is closely aligned with what Brent had just talked about. So a lot of computer vision mapping tasks. So we're also focused on our new iteration of DeepSeg around rapid experimentation and how configurations can enable that, reproducibility, and also collaboration. And surprisingly, I'm going to talk about how our configuration enables collaboration. So this is our new architecture, and previously we would have talked about these light blue data prep, train, cross-validation, and prediction stages. So what we've done to rework our pipeline is have those in overarching higher level architecture, and that has the ability to interface with PyTorch, TensorFlow, Detectron-2, and more frameworks. So one of the drivers was we have colleagues supporting people undertaking PhDs using these different frameworks, and we also see new research come out that nicely uses these different frameworks, and we want to evaluate that and see how we could use it. So we moved to an architecture that has a simple interface where we're onboarding parts of these frameworks and experimenting with them. But what became clear early on in this piece of work was the number of configuration points we have throughout all our modules and just how many configuration variables there are. So starting off this piece of work, I took a look at our options for configuring our deep learning pipeline. And what we were doing was simply using YAML files and some bespoke Python to do that. So as well as the many parameters and them being in many places, we also had a few other pain points we wanted to solve, and that was being able to extend some of our functionality and onboarding of functionality, ideally through configuration. And that includes, in the past, we had a lot of our loss functions imported and written in, hard-coded in our Python pipeline code. And we wanted to be able to ideally onboard new loss functions, metrics, even models through our configuration, and not have people using that may have identified a loss function off the shelf, having to dive into that Python code, which might be outside of their usual skill sets. And we also want to be able to override many of our functions, and often that's from the command line or ideally sweepers that might be tuning our pipeline on our behalf and making decisions about those parameters. And that fits into our goal of rapid experimentation. So what I landed on after looking at a few solutions was Meta AI's Hydra. So maybe a few of you have come across this in the past. They have this beautiful, friendly drawing of a monster. But there are multiple approaches to how you may employ Hydra. And I have had some feedback as we, for example, get into quite nested YAML, that we're going down the right-hand side path here of the more scary form of the Hydra monster. But I'm going to hopefully touch on that when we do add some complexity, we actually get a lot of value out of that. And there's more like that left-hand Hydra. So I'm just going to dive straight into some code examples. And what I'm trying to demonstrate here is through very simplistic code examples of using the underlying Hydra package for configuring deep learning pipelines, that we get a lot of value out of the box by simply employing this as our configuration framework. So what we do is we have this decorator, a Hydra decorator, and that points to a path and it points to a file, our configuration file. And once we've used that decorator, we can now access our configuration object throughout our code. So here's an example of my example config, and there's some training parameters. And here's my code, accesses that configuration object, and it just simply prints out those configuration parameters I've supplied. But straight out of the box, we get a help, and we can simply run help. Now I've got that decorator in our code, and it simply does what I had just done, much easier. Well, without any code, it tells me what those parameters I have set. And you'll notice at the top there, it's also giving me some notation there for overriding from the command line. So I can have my YAML file. So again, this is all based on YAML. I can have my YAML file, and in the command line, I can overwrite one of those parameters. And then when I run my script I had before, we can see that has been overwritten from the command line. So this concept of being able to override parameters really ties into one of the goals we had going into reworking our deep learning pipeline, is to, because we can have in some projects 100 different parameters we might have set for our pipeline, that we want to hide a lot of that from the user. And nicely, Hydra has this concept of defaults, and we can have a defaults file with a whole lot of sensible settings in there. And that's abstracted a level lower than where the user, or a less sophisticated user, may be looking, somebody that's new to our system. And so this is concept of defaults lists, and that references our defaults file. And the user might just come in there, and it's kind of self-documenting, because if you do jump down, look at the defaults file, you instantly see everything that can be configured. And then in your experiment, you'll just pull out of the defaults file that one parameter you might want to override, in this case, the number of epochs in training. And we override that setting that is in the defaults file. straight away, something that I found quite interesting was this concept of resolvers. And we had that via our bespoke Python code, a lot of different, we had a lot of manipulating handling of our configuration file. But what this does is can place a whole lot of functionality for handling our configuration of variables and manipulating those all in one place. So in this example here, I've created in this resolver file where I can add many pieces of functionality, this one method that calculates how many training instances I have, in this case, how many images I have for training in my training data sets. And I can now reference that at initiation of that configuration object once and access that throughout my code. So here we see we print that object and I have 422 images I am training on. And this is really powerful. You can just have them together and have many, many ways to handle these configuration variables. Instantly, something else that I got quite excited about it was the idea to be able to instantiate objects via the special parameter targets. And here I am in this example I want to onboard focal loss from quite a popular PyTorch library, semantic models PyTorch. In the past, we want to onboard a new function. Again, as I said, we'd have to go into the Python code, edit that, go through the source code management. And again, this would get checked eventually into source code management, but very quickly, I can add this new loss function in YAML and its arguments. And we call this special argument instantiates. And we instantiate that loss function and we can start using that in our training. So where this gets really useful is I can move that loss function into its own YAML file. So we are talking about nesting YAML now, and some of the feedback is you have to now go to multiple places to edit your configuration. And so I can have a whole lot of loss functions, metrics models, augmentation, all sorts of things under their own subdirectories. And this is where feedback has come in saying, I now have variables in so many places. There's a bit more cognitive overhead here. But I'm going to tell you why it's more like this version of Hydra, the friendly Hydra. We get a whole lot of functionality because of that structure. So we have this idea of multi-run that Hydra gives us out of the box. And here, when I'm running my same little example, I can reference those configurations, and Hydra will automatically spin up a matrix of all those. So in this case, 2 loss functions versus 3 loss functions versus 2 models, and it'll spin up trials for me running those. And that's because I have those independent, in this case, loss and model definitions. So we get that out of the box, and that's working towards our ML ops goal of being able to experiment rapidly. And Optuna was something we were using in the old version of our pipeline. This is an extension of this concept of ML ops. It's a piece of software or a Python library for being able to take that concept of multiple runs even further. So there's Hydra provides a plugin for this. So with just simply importing that and then defining some extra configuration, we now get access to that Optuna functionality. And again, if anybody is familiar with Optuna, on the right there, you'll see I've selected a whole lot of parameters for working with that. And on the bottom there, I wanted to go off and make decisions about what's working best in my deep learning project in terms of batch size. And in this case, I give it 3 values. I'm going to come back to that, but also I want to show you how easy it is to implement things like trackers. So the PyTorch Lightning project has ML Flow plugin, and that is very useful for tracking our deep learning. It puts all of our results into one place, but also it also has all of our parameters, and that supports our reproducibility. So here's the Optuna sweeper that has gone off and spun up 3 different jobs for me using 3 different batch sizes, and ML Flow has collected those results into the one place for me, and then I can jump into each of those results, have a look at all those configuration variables, have a look at some of the results from evaluating those trainings, and importantly, we can output our configuration YAML, and that can be fed back into Hydra just to rerun it again to support reproducibility. So we also have a bit of code in our pipeline that outputs visualizations. So here, by using Optuna, I've had it go off and trial 4 different models. Again, I've asked it to, I've sent one command in, Optuna's gone off, run 4 different models, and then my visualization functionality shows how those are performing to me. There's even more plugins available. One I need to get on to as soon as possible trialing is a Slim Job Launcher, so something very relevant to our use of our pipeline in NeSI. And one point on collaboration is, as our project's developing, we're getting more and more of these recipes or experiments of different uses of our pipeline, and then people that are new to the project can jump in here and see the settings and data sources and how people have used our pipeline. So it's great that people can contribute back to our source code store with some of their own solutions. And of course, our pipeline has a lot of documentation, and a lot of this focuses on Hydra, trying to get colleagues, give them this first sort of workshop use case so they can get running with our pipeline. So a lot of these benefits I've talked to, well, all of them are related to the use of Hydra, and I wanted to demonstrate that by making a decision about our configuration framework, we've got all these benefits that would have taken us a long time to develop ourselves. So it's a plug for Hydra, it's a plug for thinking about frameworks in advance before diving into development such as our deep learning pipeline. So we've got that traceability, and that was enabled by ML flow and Hydra that enables us to initiate these objects. And reproducibility, that was straightforward. We can experiment rapidly with this Optuna plugin that Hydra gives us. And we're collaborating through returning these experimentation YAML files back to our source code repository for others to pick up and use. So yeah, that's all I have. Thank you for your time.
Cool. Thank you very much. Great talk, Simon. Let's see if we've got some questions. None have appeared just yet. I'll get the lead off with one of mine. You talked about novice, or sort of abstracting away some of those YAML files for the novice. I wondered if you could speak some more to your experiences in getting your colleagues using Hydra, if you've done so yet.
Yeah, so part of me presenting today is I've got a few colleagues here, and I could have done a better job in the past explaining some of these benefits that I have just now, and this has been a good opportunity to do that. So I'm hoping by running through this, and I run through this again with more of my colleagues, that I can show to them that we are getting all these benefits straight out of the box. And I know when people have gone into the source code repository, it can be quite scary that there's this huge scattering of YAML files, and where do I jump in and which ones do I edit? And I fully understand that, but at the same time, I have found personally, and I have been working this way for quite some time now, since I've come across Hydra, and I've personally found because of the out-of-the-box functionality, it far outweighs that little bit of cognitive overhead in terms of having the nested YAML. And it doesn't necessarily have to be nested in terms of other files. You can actually add it all into one file and have it all in there, which I'm working on my preferred way of working, which is actually nesting them. So hopefully people can see the benefits of this.
Cool. I've got a question here. Thanks, Simon. Great talk. Is Hydra machine learning specific at all? Also, does it give any way to discover the source within all of the YAML files of where the particular final config value came from?
What I understand it was designed with deep learning projects in mind, and specifically with the sheer number of parameters these deep learning projects can have, and that's where a lot of the decisions about functionality have come from. I don't know the answer to that second part of that question. That's a good question. No, I guess you do have a lot of, no, sorry, you do have a lot of dot notation. So when I run that help, you would have seen, and as well as help, when I run my pipeline, I log out to our logs the the Hydra configuration, and through that dot notation, we can actually follow the path down to where each parameter came from. So yeah.
I suppose a slight follow-on from that would be, do you version control the YAML files with all the parameters for a particular run?
Yeah, we haven't got there yet, but we have talked about how, and especially same as with our source code being under development, how we should be version controlling this for that reproducibility. So that is something we still need to get to.
Cool. We've got another question.
But actually, just to add to that, we do write out that to MLflow, that config.yaml, which is a static store of that configuration.
Okay, cool. So we got very nice talk with the resolvers. If I understood well, does the YAML doesn't start to implement a mini language of itself? Also very nice to see how this integrates with other open source tools.
We'll have to think about it if I'm understanding the question right. But when the resolver is called, there is this dollar syntax that is calling the resolver, which is running that Python in the background. And there are extra arguments around the resolvers, whether you want that to be cached or ran each time. So in many cases, you want that just to be executed when you first create that configuration object. But there are the cases where you may not want that to be static, and each time that you call the actual property of the configuration, it will run that resolver again.
Cool. That seems to be all of our questions for now. So I'll thank you again for your excellent talk, Simon. And we're sort of hitting the very end of the day. So I'd just like to thank everyone that was involved in the presentations this afternoon and this morning. And I will remind you all that we start again tomorrow at 9:30. So enjoy the rest of your day, and we'll see you tomorrow.